For over a century, high-performance automotive design has centered on a single, uncompromising rule: weight is the enemy. Every extra pound makes a car slower to accelerate, harder to stop, and more difficult to throw into a corner. For decades, European legacy brands built their reputations on stripping mass away. They obsessed over forged aluminum and carbon fiber, creating low-slung, rigidly mechanical machines where lightness dictated speed. Then, BYD launched its ultra-luxury sub-brand, Yangwang, and introduced the U9. From the outside, it has the aggressive proportions of a traditional supercar, but under the skin, it weighs a massive 2,475 kilograms. That is nearly 3 tons of mass. To compound that weight penalty, engineers rejected the industry standard. Instead of using lightweight ternary lithium cells typical for high-performance vehicles, they installed an 80 kilowatt-hour lithium iron phosphate, or LFP, blade battery. LFP chemistry is heavy, but highly thermally stable for prolonged track use. By all the old laws of mechanical physics, a vehicle carrying that much bulk shouldn't be competitive. Yet, a version of this exact car recently shattered the 300-mile-per-hour barrier. The U9 didn't reach those speeds by conforming to traditional aerodynamic or weight-saving methods. It achieved them by using brute-force digital computing to turn its heaviest physical disadvantages into highly calibrated weapons. The first major engineering hurdle was straightforward. How do you violently accelerate a vehicle hauling 2.5 tons of metal and battery cells? This top-down schematic illustrates BYD's E4 platform. Instead of a heavy central engine, an independent motor sits directly at each wheel, enabling independent torque vectoring. As the vehicle enters a turn, the outer motors spin faster while inner wheels brake, forcing the chassis through. Together, those 4 independent motors generate 1,287 brake horsepower and 1,680 newton-meters of torque. That output propels the U9 from 0 to 62 miles per hour in 2.3 seconds. By entirely digitizing how power is delivered to individual contact patches on the road, the E4 architecture effectively renders traditional mass-based acceleration penalties obsolete in a straight line. Acceleration is one thing, but keeping a heavily weighted vehicle from flying on dusty asphalt during high-speed cornering presents a different problem entirely. Traditional coiled metal springs simply cannot manage that much lateral momentum. To solve this, the U9 uses the DiSus-X system. This cross-section shows a kinetically driven hydraulic actuator replacing the traditional spring. When cornering, it lifts at 500 millimeters per second, instantly generating a ton of counterforce to keep the heavy body perfectly flat. When the U9 first appeared online, videos of the car jumping entirely off the ground from a standstill or driving smoothly on only 3 wheels went viral. These public stunts were direct, real-world demonstrations of this highly precise suspension control. DiSus-X is the critical piece of software-driven code that actively manipulates the car's immense mass, tricking a 2.5-ton object into handling like a featherweight track car. By late 2024, BYD moved past consumer demonstrations and aimed for serious global motorsport credibility, taking the platform to the brutal validation grounds of the Nürburgring. The data gathered on that German track led to the development of a highly focused 30-unit production run unveiled in 2025, the Yangwang U9 Xtreme. This chart highlights the massive scaling potential of digital platforms. By upgrading to a 1200-volt architecture and pushing the motor limits to 30,000 RPM, the U9 Xtreme more than doubles the standard model's output, reaching 2,978 brake horsepower. Those upgrades translated directly to the pavement, clocking a blistering 6-minute, 59-second lap at the Nürburgring. Shortly after, at the Papenburg testing facility, driver Mark Bassing pushed the car to a one-way top speed of 308.4 miles per hour. These figures prove that electric, software-defined architectures possess a performance ceiling that is vastly higher and much easier to scale than strictly mechanical drivetrains. Strict international standards excluded that 308-mile-per-hour run from official production cart speed record lists because the test was conducted in only a single direction, rather than taking a bidirectional average. Regardless of the certification technicality, the mathematical reality stands. An electric vehicle successfully crossed the 300-mile-per-hour threshold, easily eclipsing the raw velocity metrics of highly celebrated combustion hypercars. In a few short years, the vehicle evolved from a heavy, unconventional engineering prototype into a globally recognized cultural flagship for modern electric performance. That status was cemented in April 2026 when the supercar was officially added to mainstream racing simulators like Gran Turismo 7, placing it directly into the hands of millions. The Yangwang U9 demonstrates that extreme weight is no longer a disqualifier for performance. It proves that by combining heavy-duty batteries with high-speed processors and quad-motor control, software can effectively neutralize the physical disadvantages of a 3-ton curb weight.